As we continue our explanation of trigonometric form of complex numbers, one of the things that we've been working with is finding the nth roots of any complex number. So I've got the complex number negative 2 plus 2i displayed for you. And I want to convert that over to the trigonometric form of a complex number before we can find the nth roots of this. So one of the things that I need to know what the magnitude of this is. So the magnitude of this particular number, if we use the Pythagorean theorem, knowing that the sides of this triangle here are negative 2 and 2, then the magnitude of our vector is the square root of 8. The angle of reference then goes from 0 over to our vector, and that particular angle is in degrees is 135 degrees. I'm going to work with degrees here because I want to make sure you guys are clear exactly what we're referencing here. I've now included the formula for finding nth roots of a complex number, and I've converted it over, so instead of having a 2 pi written, which would be used if we're dealing with an angle measure in radians, I've written in the 360. Just a reminder, because this problem we're going to search for, let's search for the 3 cube roots of negative 2 plus 2i. So that means that n is going to be equal to 3. R is what our magnitude is. That's going to be equal to the square root of 8. Our value of k goes from 0 to n minus 1. So that would be 0, 1, and 2. And then theta is our reference angle. Theta is going to be equal to 135 degrees. So what I need to do now is I need to set up our expression, substituting in these values all 3 times. For when k equals 0, for when k equals 1, k equals 2, and then solve the expressions. I've substituted in unknown values for n, r, theta, and k equal to 0 to start with. Now I need to simplify this. This is going to simplify to the square root of 2 times the cosine of 45 degrees plus I times the sine of 45 degrees. This is further going to simplify down to cosine of 45 degrees is the square root of 2 over 2. So when I multiply that times the square root of 2, I get 2 over 2. And then I have plus I. The sine of 45 degrees is the square root of 2 over 2. When I multiply that times the square root of 2, I get 2 over 2. And our final answer is going to be 1 plus I. The second root is found by taking the cube root of the square root of 8 times the cosine of 495 over 3 plus I sine of 495 over 3. We get the 495 by substituting 1 in for k. So I have 135 degrees plus 360 degrees, which yields us the 495. Simplifying this, I'm going to get the square root of 2 times the cosine of 165 plus I sine of 165. Now this is going to be a bit of a decimal approximation here. And I'm going to end up with negative 1.366 plus 0.366i. The third root of our solution then comes when we substitute in 2 for k. Simplifying the expression, then I end up with the cube root of the square root of 8 times the cosine of 855 over 3. 855 over 3 then is going to simplify to be 285 degrees. So again, I'm going to end up with the square root of 2. This will be the cosine of 285 degrees plus I sine of 285 degrees. Entering those values into your calculator, this is going to be approximately equal to 0.366 minus 1.366i. The last thing to note here is where our solutions of our nth roots, where they actually lie on this circle. This circle is similar to a unit circle, except instead of having a radius of 1, we actually have a radius of the nth root of r, which for this particular problem was the square root of 2. So our radius is the square root of 2. Our first solution came from the 45-degree angle and was 1 plus I, which is right here. And I'll draw a vector to that particular point. Our second solution then came from an angle of 165 degrees, which is analogous to our solution, which was estimated at negative 1.366 plus 0.366i. And our last solution is analogous to an angle measure of 285 degrees and has a complex solution of 0.366 minus 1.366i. If you pay attention very closely to these solutions, they do look like they are placed symmetrical on this particular standardized circle. Coincidence? I don't think so. In the meantime, thank you so much for choosing in, and look for example number 2, where I will show you another example of how to find the nth roots of another complex number.